Treaty 7 territory, land colonized as Canada. My name's Ryan, and on Wednesdays I do live streams where I'm working through the basics of math and physics, also statistics the from my new vantage point, from my new background as a somatic educator and a former vocational scientist that maybe didn't attend to myself the best as I went through this material. And then also getting to review it is great. So you can review along with me. Um, Feynman Lectures hosted at Caltech. You can see the URL top of that browser. And we're on chapter 11 today, vectors. Yeah, so this is a little bit of a slower, more delicate type of session where I take my time with the material and maybe get confused on camera and sit here and stare into the void a little bit. And if you do want to interact with me, I'm monitoring 3 platforms right now: YouTube, Vaughn.live, and Twitch. A little bit of an echo there because I don't need to monitor with the sound. Okie dokes. So, yep, that's the situation. If you have any questions or feedback as to the material, or maybe what I ought to be doing to be a little bit more comfortable on camera, then go ahead and chime in. Otherwise, we'll look at this chapter 11 in the Feynman Lectures, volume 1, that is, starting off with symmetry in physics. Offers a definition of symmetry from Weyl, W-E-Y-L. If one can subject it to a certain operation, and it appears exactly the same after the operation. So it's a group theory, I think, is the basis of Weyl's models. Feynman says, suppose we build a complex machine in a certain place with lots of complicated interactions and balls bouncing around and forces between them and so on. You build the exact same equipment in another place, everything the same but only displaced laterally by some distance. If we start the 2 machines in the same initial circumstances, we will ask, will one machine behave identically to the other? Will it follow all the motions in exact parallelism? Of course, the answer may well be no, because if we choose the wrong place for our machine, it might be working inside a wall, and interferences from the wall would make the machine not work. So you couldn't translate it arbitrarily. It needs to be in an equivalent situation. Some common sense. Then Feynman tries to repair the question. If we define things well enough that the essential forces are included inside the apparatus, all the relevant parts are moved from one place to another, will the laws be the same? Will the machinery work the same way? One move the equipment and all the essential influences, but not everything else. And then the machine will work the same in one location as another. So there's a number of laws of physics that are invariant to translations, I think is the point. Bring us to translations. And so we've got the Force laws, guess the second law, force is mass times acceleration, written out in the x, y, and z components. Where do we put the origin of our coordinates? Yeah, in Feynman's synopsis on Newton, I'll read again a quote. All that Newton would tell us at first is that there is some place that we can measure from, perhaps the center of the universe, such that these laws are correct. But we can show immediately that we can never find the center, because if we use some other origin, it would make no difference. I think that's the Galilean relativity. It's going to work out. Joe has an origin in one place in Mo. Origin some other place. Figure 11.1. Joe and Mo. Let's take a look at Joe and Mo. Standing x distances apart. Sorry, a distance apart and x distance from some other quantity. Some point in space. Yeah. So they have x and x prime. They have different distances. We can express x, y, and z and x prime, y prime, and z prime. The apparent distances. The labeling, I think, of this x-axis is a little tricky. I think this is the distance x. This is labeling the coordinate x, like here, y, by the head of the arrow. And then I don't know why x prime is on the end of the x arrow exactly. It's showing that you could have a second frame of reference anchored on Mo. And so if this is x units of length, a different x in here, then this is x prime because it's x plus a. X prime is x minus a. Yeah. Hmm. I said x plus a, but it's a very basic thing that I've got backwards here. Let me read through this, see if I can get oriented on how the words are being used. I guess it shouldn't matter if it's plus or minus a when I think about it. Because all we're assuming is that there's a difference between them. All right. So if Joe knows Newton's laws and Mo tries to write them down, will they be correct for him? Does it make any difference from which origin we measure the points? Is it or not true that mass times the acceleration measured in, say, Mo's frame is equal to the forces in Joe's frame? Oh no, sorry, they're the same. Sorry, no, they're both in the relative frame. Yeah, those are primes there as well. So okay, so Joe is the XYZ frame. Right, are they also correct for Mo? Yeah. Okay. So so x prime is x minus a. So the derivative of that can be separated into the difference of the derivative of those two things, the change. So dA, you're right, it's a fixed difference in their position. So d8 by dt is 0. And find that the dx by dt are the same because it's just shifted by, right, the rate of change is the same. So the acceleration is the same. Symmetrical for translational displacements, they do not change. It's interesting and entertaining to discuss the math of it. So the translational displacement, at least for a static displacement, then that's obvious, yes. And maybe slightly entertaining. Okay, so 11.3 rotations. So it should make no difference which direction we choose the axes. So you can set up your x, y, and z. As long as they're orthogonal to each other, they can be oriented anywhere. Gets hung up on pendulum clocks because you need to keep the orientation of the pendulum with respect to the Earth constant. Okay, I'm going to read this discussion more carefully about the clocks. I'm not skimming it well. Okay, so points out that the rotation of the Earth allows you to do this experiment and see that the pendulum clock is maintaining a constant function. It's not true that as we turn a thing, it follows the same laws as when we're not turning it. If we perform sufficiently delicate experiments, we can tell that the Earth is rotating, but not that it rotated. Hmm. So its angular position isn't absolute, I think is the point. So we've got two coordinate systems for Mo and Joe. They're now at the same origin, but Mo is tilted theta degrees above the horizon of Joe. So its y-axis is tilted back theta degrees of the y-axis. And there's a bunch of constructions. Let's read the description. There's a point having coordinates x and y in Joe's world. There it is, P. And that corresponds to x prime and y prime in Mo's world. So start off by expressing x prime and y prime in terms of x, y, and theta. And to do that, you draw perpendiculars to all four axes and draw AB perpendicular to PQ. Let's see here. Where's Q? I see. Right, so by drawing a line from P parallel to the x prime axis, you get Q, which tells us the y prime value of point P, and same thing with going parallel to y prime and intersecting the x prime axis to get the x prime value. And it's A and B. Hmm. Right, so A is the x value on Joe's axis. And then if you connect A and B, this is yeah, a little different for me. So that perpendicular then is the thing we're going to talk about. X prime could be written as the sum of two lengths along the x prime axis. Y prime is a difference. Right. The part left, the line segment Q to B, and then the line segment B to P. So this part on X prime and then this part on X prime. Hmm. Yeah, I'd like to work this out for myself from scratch. Part of it is seeing all the places that theta shows up. X cos theta plus y sine theta. Yeah, I can like find because everything looks like it's a theta-like angle or its complement to 90 degrees or 90 degrees in this diagram. So I can assume that's theta here, and then I see how this is. Oh no, sorry. Then this would be y sine theta, not that whole length there. So what is that triangle? Hmm. Yeah, I could spend some time actually trying to figure this out better. If I play the recording in the background, that would be interesting sound while I try to make sense of this diagram. I guess given how Facebook reacted to when I listened to local university radio and played that in the background one day, I might not want to poke them in the eye with any kind of recording online. So yeah, I won't play the lecture. You can play it. In this figure, I just don't see the triangle constructed, that this is the sign, this would correspond to the opposite side of. If this is 90 degrees, yeah, here, yeah, I don't see it. Yeah, and because this triangle here is a right triangle with angle, I would think from the origin to this point here is x cos theta. Oh, maybe this isn't labeled perfectly, then that would make sense. If it was from there to there is x cos theta, because, oh no, right, sorry. I should actually, so I'm doing this little triangle. Sine theta is opposite word hypotenuse. So hypotenuse is equal to opposite sine. Yeah, cos theta, adjacent over hypotenuse. So hypotenuse. Right, it's the hypotenuse you want. That's equal to, oh no, the adjacent over cos theta. Hmm. Hmm. I'm a little stuck here. Hmm. Anyone tuning in to watch this paint dry? Hi, everybody. Hello, out there. Okay, so how to make progress here. I want to figure this out better. I don't just want to blow by it. It's a very simple thing. It should be a simple thing um, that I can't seem to figure out right here. Let's see here. Copy image, copy image. Go over here. Yeah, just invert this. Yeah. Hey, now I can play with it. Okay, so we're just trying to find x prime and y prime in terms of x and y. Uh, not completely sure what I'm hung up on even. But let's see here. So the x value from P we get from point A here, and we can make this triangle by finding the perpendicular along from there to there. Yeah, okay. Not articulating it very well, but I can see it. Um, So isn't this theta, this angle? Right, this distance here is being written as two distances. So this is theta. This is a right triangle. So well, why won't that actually draw something? To drag it? It's inconvenient. So that's A. This is, we'll call this Y. This is theta. And so this is the hypotenuse of that. It's not what Feynman's talking about. This is also a right angle. Is this angle also theta? The sine of this little triangle here, sine theta. No, sorry. Just assume I need to get the cos of the theta. So the adjacent over the hypotenuse. So x over h. So therefore h to the x cos theta. But that would be this distance here. And then this looks here like it's theta. Let's assume that's right. Then this here, y prime, but I don't know. Oh yeah, this looks like it's 9 degrees. Okay, so if I'm oriented right anyway, then this is the hypotenuse. If this is y over here, then y sine theta is this length. Why would that also be y? Why is this whole thing here? Yeah, so I mean, that's the second triangle I want to draw. I don't know if it's right. Might as well get it down, like permanently, forever. But it looks like this is the second triangle. That is 90 degrees. That's theta. And then this segment would be y sine theta. Oh yeah, that's right. If if this is y, no, sorry, no, that's still not right because y is this whole length here. Yeah, so I can see a triangle or two that might be congruent, but it doesn't mean I'm seeing the actual right, the correct geometry here. the extra distance that we need to add on to the hypotenuse of this triangle looks like this thing over here. Looks like the same thing. So you can kind of see how they have to be, they're congruent. Well, yeah, it's the parallel lines theorem, right? They're the same angle formed by the same set of parallel lines. So can I see it easier here? So this is why. That's why. Uh, okay, yeah, put y in a better location. So this is why. Just call this A. Call that H. Wait, why do we even want H? We want part of H. Hmm. Sine theta is equal to opposite over hypotenuse. So the hypotenuse is equal to A over sine theta, right? That's still not what we want. We want this thing anyway. Oh no, we want this thing. That isn't some y value, that's some other value. So back to this triangle. So it's the same argument that this is also theta. I realize now we have parallel lines there and there and there and there. So this is theta. That's 90 degrees there. So we could find this. Could be the thing we want. This would be the hypotenuse of this triangle. This is what we want. With the clue that it's a sine relationship. Sine theta, it's the same thing. I want to solve for A. It's kind of more obvious over here. Okay, it is this. So what is that? Well, Feynman's saying A is Y. Well, why is this whole thing? Okay, well, I've been around it a couple times and I'm stuck in the same way, I think. Um, yeah, admitting defeat moving forward. Can't wrap my head around that completely. So we analyze the forces. It works out the same for the forces when you do the force analysis. So for the left side of this equation, we're actually differentiating those equations um, for the position in the in Mohs coordinates. So these are the 11-8 things. Let's see if I remember how to do that. So we had, it's a little much. The force in the x position. We're talking about x prime. And x prime. Oh, we didn't really have it as time dependent. The position. Okay, I can't scroll down. Right. Well, no, it's a product rule. So just write product rule. Am I doing this right? Shoot. I forgot my derivatives. I need to look them up. All these should be thetas. Doesn't matter. But that's only one of the terms. And F. The other term was right, x is our variable. It's, y sine theta. So then the derivative of that make a t is y cos theta minus sine theta, no, plus sine theta. And the second derivative, so y negative sine theta plus cos theta plus sine theta. It's pretty different. And then 2 sine x plus x. Sum. Let's write it out. Sine theta minus y sine theta plus cos theta minus 2 sine theta minus x. What is the x cos y? What do x cos theta must be? So yeah, can I group that? So that's group the sine thetas. Sine theta minus 2 sine theta minus, well, okay, plus cos theta minus x cos theta plus minus y cos theta sine theta. Shoot. Didn't even group that right. Minus 2 sine theta minus y sine theta. That's it, apparently. plus cos theta minus x cos theta. Okay. So negative sine theta minus y sine theta plus, I'll factor this one out as I go, cos theta 1 minus x. Here I can factor out negative sine theta 1 plus y. I don't feel like this is very close to what Feynman has. Maybe if I massage it more. Yeah, has kind of symmetry to it, but yeah, I don't recall it looking like that with Feynman worked out. Nope, not at all. Well, it's practicing something live. It's been a tedious, difficult day. And anyway, when Feynman does it, behold, the right sides of the two equations are identical. Rotating your axis shouldn't matter either. Ta-da! Then more generally onto vectors. So the boldface symbol R is going to represent the three numbers, x, y, z, to specify the point in space. Without concern too much about the convention. Any physical quantity associated with the three numbers which transform, as do the components of the step in space, is a vector. The rules for adding vectors. Subtraction. Pretty simple graphically. Differentiating a vector in time gives you another vector. Seems intuitive, but said. Newton's laws in vector notation. So the acceleration is written in components x, y, and z, and as the second derivative of the spatial definitions. F equals ma. It's the same as F as the product of the mass and the second derivative of the position. Here's apparently a complicated example. Particles moving on some complicated curve. Exists in T1, it has a velocity V1 or nu one. It's in T2 later. It has different velocity. So what's the acceleration? We need a difference in the velocities. How do we get the difference in the velocities? We subtract the vectors. I see. So if you take the second vector and subtract it from the first vector, you get this. but that isn't the acceleration. The tails of the vectors aren't in the same place, so we can't subtract that way. Hmm. So the two vectors need to have the same origin. The angle between them is figured out. This is the same similar construct to what we were looking at before. This lets you figure out the actual change in velocity between them. Hmm. All right. Well, maybe the least interesting thing of watching this is when I fuzz out and lose my focus. But yeah, I think I need a break, and we're coming up on the, the noon hour mark, close enough. I think I'll call it today and maybe revisit some of this next week. Maybe after I've had some more quiet time with myself to figure it out. Um, so yeah, that'll be it for today. Um, you're welcome to send questions or comments wherever um, you see fit. Um, find me through my practice site, Somatica. And yeah, tomorrow continuing with the movement organizing theme, something more relevant to somatic educators or people that are interested in thinking about moving more comfortably or maybe practicing some things to move a little bit more comfortably or to negotiate things a little bit more diplomatically for oneself. Thanks for coming along.